Fingerprints are the most infallible means of identification. For this reason, the forensic scientists usually rely on this technique to pin the criminal. Whenever a finger comes in contact with any surface at the crime scene, it may be a wall, it may be a piece of furniture, it may be a door or a window, the person leaves a residue of sweat which is called latent fingerprint. It is not visible, that's why it is called latent, which means a hidden fingerprint. However, sweat contains a large number of chemicals. They may be inorganic, they may be organic, it may be water also. What we as fingerprint researchers do is that we choose a particular chemical and by some physical or chemical means we render visibility to it, we make it colored. Generally, the physical method is the adsorption method, that a particular colored compound becomes adsorbed on the oily or the moisture content of sweat and imparts color to the latent fingerprint and makes it visible. Under chemical methods, it's basically a reaction, a chemical reaction. For example, ninhydrin reacts with proteins and amino acids to give a purple colored compound called Ruhmann's purple, so that the colorless amino acids and the colorless proteins are converted into a purple color derivative. Nile Red is another reagent which has been widely used for detection of latent fingerprints. It does not follow the previous two techniques. It neither gets adsorbed nor it reacts. It's a lipophilic dye. That means it becomes attached to the lipid content of sweat, and the attachment is controlled by thermodynamic factors. Let me clarify, it is not simple adsorption. We use a solution of Nile Red. It mingles with lipophilic components of sweat, the lipid, the fatty acids and the higher proteins. It mixes with them and it gets dispersed. The dispersion is controlled by entropy effect, and that's why I said it's basically controlled by thermodynamic parameters. The entropy of the system increases and Nile Red imparts red color to the sweat content and makes the fingerprints visible. The advantage of this technique is that it can be used both on porous as well as non-porous surfaces. Yet another advantage is that fatty acids and lipids are water insoluble in nature. Therefore, even if the surface is wet, sharp and clear fingerprints develop by a ninhydrin method. This is important because these days many criminals try to despoil the crime scene after committing the crime by spraying water over it. By conventional techniques, it's not possible to detect fingerprints on moist surfaces. But since, as has been said, Nile Red tags the insoluble components of sweat, therefore even if the surface is moist, even if a criminal attempts to despoil it by pouring water on it, fingerprints can still be developed. The technique is very simple. All that is required is a dilute solution of Nile Red and a light source. Nile Red is fluorescent in nature and therefore under ultraviolet light, sharp and clear fingerprints can be visualized by this method.
Dear students, after studying this module, you shall be able to know that the Nile Red reagent develops latent fingerprints on dry and wet porous surfaces. The Nile Red may be used as a post-treatment reagent for staining fingerprints developed by cyanoacrylate fuming. The Nile Red tags insoluble lipid and fat constituent of fingertip sweat to reveal red-colored ridges. The phenomenon by which Nile Red detects fingerprints is guided by thermodynamics considerations. And lastly, you will learn the merits and demerits of the Nile Red technique of fingerprint development. Let us start with the introduction. Finger marks on porous surfaces like paper can be extracted using treatments that target compounds like amino acids or lipids derived from skin secretions. But detecting finger marks on non porous material and in wet or humid conditions is more complex and poses a number of challenges, particularly on dark and patterned material where results often lack sufficient contrast. The compound Nile Red is currently used, providing investigators with both contrast and photoluminescence. Nile Red is a lipophilic dye, which means that it stains fat and lipid components in biological samples. It is also used to stain oil and wax to a red hue. Nile Red, also known as Nile Blue oxazone, is produced by boiling a solution of Nile Blue with sulfuric acid. Nile Red stains intracellular lipid droplets red. In most polar solvents, Nile Red will not fluoresce. However, when in a lipid-rich environment, can be intensely fluorescent, with varying colors from deep red to strong yellow gold emission. Its structure is depicted in the given figure. Nile Red is used to detect latent fingerprints on dry and wet porous items like paper and cardboard. Although the physical developer can also lift latent impressions from wet porous surfaces, the method is a multi-step one and requires immersion of delicate paper-like articles in a sequence of working solutions. Compared to that, the operational steps of Nile Red method are real simple. The reagent develops clear, stable, red-colored fingerprints which may be discerned in natural light. On non-porous items, Nile Red is used as a post-treatment reagent to enhance the fingerprints developed by cyanoacrylate fuming. Let us discuss synthesis. Historically, Nile Red was prepared by acid hydrolysis of the dye Nile Blue. Nile Blue A has been used to enhance cyanoacrylate fume prints but has never been used as a stain to visualize native prints either on porous or non-porous surfaces. It is known Nile Blue solutions contain impurities of Nile Blue oxazone, a degradation product resulting in different chemical staining properties. Alternatively, Nile Red and its analogues can be prepared by acid catalyzed condensation of corresponding 5-dialkyl amino 2 nitrosophenols with 2-nephthol. The yields are generally moderate as no co-oxidant is used in this procedure. Since the reaction to generate Nile Red does not usually exhaust the supply of Nile Blue, additional separation steps are required if pure Nile Red is needed. Now let us have a look on theory. The chemical entities present in fingerprint residue may be broadly classified into two types. Number 1, water soluble, and number 2, water insoluble. the amino acids and inorganic ions such as sodium, potassium and chloride belongs to the water-soluble class. The water-insoluble class includes proteins, lipids and fats. In order to gauge the pathway by which Nile Red detects fingerprints, it is pertinent to further subdivide the water-insoluble category into two fractions. Number 1, the robust fraction, which includes proteins and peptides, and the labial fraction, which includes fatty acids, triglycerides and lipids. Whereas the physical developer interacts with the robust fraction components of sweat residue. Nile Red tags the labial fraction entities. The labial fraction is so named because its components undergo rapid chemical transformations. This fraction is soluble in non-polar solvents like hexane and petroleum ether, but sparingly soluble in polar solvents like water and methanol. A chemical reagent which fixes the labial fraction of sweat residue for developing latent fingerprints should not be dissolved in a non-polar solvent. Otherwise, the solvent will wash away the labial components before these have a chance to interact with the developing reagent. It is for this reason that Nile Red is dissolved in acetone. On coming in contact with the labial components of the fingertip sweat, the stain partitions between the original solvent in which it is less soluble and the fats or lipids in which it is more soluble. The molecules of Nile Red get preferentially dissolved in fat and lipid components and impart red color to these biomolecules. The preferential solubility of Nile Red in fats and lipids is a physical phenomenon which is controlled by thermodynamic considerations. As the molecules of Nile Red become dispersed in the lipophilic media, the entropy of the system increases. Entropy is a measure of disorder in a closed system. Greater the degree of disorder, greater is the positive value of entropy and more stable is the system. When Nile Red becomes dissolved in fats and lipids, its molecules become randomized in the sweat residue, thereby increasing the entropy. The fallout is that the red color imparted to the fingerprint residue is more intense than that of the original stain. The outcome is that clear red colored ridges become visualized. Now let us discuss the methodology. Two test solutions are prepared when fingerprints are to be detected on dry or wet porous items by Nile Red reagent. A. Stain solution. It is prepared by dissolving 1 mg Nile Red in 1 ml acetone. B. Working solution. It is prepared by dissolving 100 ml of stain solution in 99.5 ml distilled water. As a fingerprint reagent, Nile Red may be used either as a lipid stain or as a post-treatment dye to enhance cyanoacrylate developed prints. Let us discuss the first condition as a lipid stain. The evidence bearing latent fingerprints is placed in the working solution for 10 to 20 seconds. For older prints, the immersion time may be increased to 30 to 40 seconds. The item is transferred to distilled water and gently agitated for about 5 minutes. It is then allowed to dry under natural conditions. The print is illuminated with radiation of 490 nanometer wavelength and observed through a 555 nanometer viewing filter. Then comes the second condition as post-treatment reagent. The article on which fingerprints have already been developed by cyanoacrylate reagent is placed in working solution for about 1 hour. It is gently and consistently agitated. Next, it is placed in distilled water for about 5 minutes. After natural drying, the fluorescence is observed exactly in the same manner as for the lipid stain procedure. Now let us discuss the assessment of Nile Red method. The Nile Red reagent develops optimum quality fingerprints on different varieties of paper. The developed prints are clearer as compared to those processed by oil red O reagent. Moreover, the shorter development time and a fewer experimental solutions make the Nile Red method a perfect one. Here, the given figure shows a representative fingerprint developed on paper by Nile Red. Nile Red can develop fingerprints that are about 15-week old, as well as those which have remained immersed in water for about 4 weeks. There is less background staining with Nile Red than with the physical developer reagent. The fingerprints developed on recycled paper with Nile Red reagent, however, are quite diffused. On non-porous items and as a post-treatment reagent, the quality of prints developed by Nile Red is lower than the processed with rhodamine 6G. Dear students, now let us summarize this chapter. So, after reading this chapter, we have learned that finger marks on porous surfaces like paper can be extracted using treatments that target compounds like amino acids or lipids derived from skin secretions. The compound Nile Red is currently used, providing investigators with both contrast and photoluminescence. Nile Red is a cytochrome dye which has been used for staining lipoprotein. It develops red-colored fingerprints on dry and wet porous items. The process is simple and involves 3 steps. Number 1, staining. Number 2, rinsing. And number 3, which is the last one, is drying. The quality of developed prints is up to the mark, provided that the impressions are about 15 weeks old or have remained immersed in water for about 4 weeks. The technique involves fewer steps and is less time consuming as compared to oil red O or physical developer methods. We have also studied that Nile Blue A has been used to enhance cyanoacrylate fume prints but has never been used as a stain to visualize native prints, either on porous or on non-porous surfaces. Alternatively, Nile Red and its analogues, for example, naphthoxazine dyes, can be prepared by acid catalyzed condensation of corresponding 5-dialkyl amino 2 nitrosophenols with 2 naphthol. And lastly, in this chapter, we have learned that as a fingerprint reagent, Nile Red may be used either as a lipid stain or as a post-treatment dye to enhance cyanoacrylate developed prints.